Alright, let's do our first example using the equations we derived in the last video. We used those equations, the Darcy-Weisbach equation, to find out frictional head losses. In this problem we have a tank and the water level, or actually the fluid is kerosene. It's kerosene. The kerosene is filled up to the height h, and the specific gravity of kerosene is 0.8. And they give us the kinematic viscosity nu of the kerosene, which is 3.0 times 10 to the negative 6 meters squared per second. And down here at the bottom of the tank we have a pipe. It's 30 degrees below the horizontal here. It's a length of 3 meters and a diameter of 4 millimeters. Okay, and up here they give us a conversion factor. 1,000 liters is equal to 1 meter cubed. And the question says, consider the flow of kerosene out the inclined reservoir tube, neglecting any entrance losses and assuming steady flow. Determine A, the flow rate, Q, in liters per minute, for a height of 50 centimeters, and determine whether the flow is laminar or turbulent. Okay, so for a height of 50 centimeters, they want the flow rate for a height of 50 centimeters, and they want us to figure out if the flow in this tube here is laminar or turbulent. Okay, and down here, actually let's label these points. I'm going to label this up here point 1, down here point 2, and notice here we have a free jet, right? It's just the water is just coming out, so that means the pressure here is going to be equal to 0. Now if we set our datum down here at point 2, we'll say that's our datum down here at point 2. What we do know so far is that the length of the pipe is 3 meters. Okay? We know that the diameter of the pipe is 4 millimeters. We know nu of the kerosene is 3.0 times 10 to the negative 6 meters squared per second. We also know that the specific gravity of the fluid is 0.8. Okay? Now, our equations, we will be able to use equation, I'll call this equation 1, the Reynolds number, is equal to the average velocity in the pipe times the diameter over nu, the kinematic viscosity. And remember they said determine if it's laminar or turbulent, and we don't know, right? They want us to figure that out. So when we don't know if a flow is laminar or turbulent, we can always assume that the flow is laminar and then check it with the Reynolds number. So let's assume it's laminar, and remember the frictional head losses for laminar flow is 32 times nu times L, the length of the pipe, over gravity times d squared times the average velocity. I'll just call it velocity A for average. And this is for Reynolds numbers that are less than 2,000, meaning this is laminar. So we assume it's laminar, and if we find out that the Reynolds number is less than 2,000, our assumption was right. It was laminar. If we find out that it's over 2,000, it's turbulent, and our assumption was wrong. Okay? So let's just begin with the equations we do know for, I'll do part A in this video. They want us to figure out the flow rate, and in order to figure out the flow rate we need the velocity in this pipe. So we can use, let's take a streamline from 1. We can take 1 all the way to 2, and we'll say the total energy head coming out minus the total energy head coming in is equal to the summation of all the pump heads minus the summation of all the turbine heads minus the summation of all the frictional head losses. Now, in this system, there's no pumps and there's no turbines, so we can say this is 0 and that's 0. Okay? And out in, which is points 2 and 1 respectively, we can say the V2 squared over 2G plus the pressure at 2 over gamma plus the height at 2 minus the velocity at 1 squared over 2G plus the pressure at 1 over gamma plus the height at 1 is equal to the sum of all the frictional head losses. And here we only have one pipe, so there's only going to be one frictional head loss. And remember, we assumed it to be laminar, so we just plug in HF into this equation. So it'd be negative, right, there's a negative, 32 nu L over GD squared times the average velocity. Okay? Now, the velocity at 2 we don't know. The pressure at 2, well, it's 0 because it's a free jet, so that's equal to 0. Now, the height at 2, well, we set the datum at 2, so we can say the height at 2 is 0. Velocity 1, well, the velocity up here is 0 because it's open to the atmosphere. Well, not because it's open to the atmosphere, it's 0 because point 1 isn't really moving, so we can say velocity at 1 is 0. Now the pressure at 1, it's open to the atmosphere, right? So there's no pressure. There's just 0 pressure. The height of 1. Okay, so, oh, and one more thing. We can say that the velocity average in this pipe is roughly the same velocity as the exit velocity. So we can say V2 is equal to VA. Okay? Now let's rewrite this. We can say V2 squared over 2G, okay, 0, 0, minus H1 is equal to negative 32 mu L over GD squared times VA, or V2. And our height, would you agree our height from the datum to point 1, it would be 3 meters sine of 30, right, which is this height up here, so 3 sine 30 plus h, okay? So we can say V2 squared over 2G minus height 1, which is the height from the datum to point 1, which is 3 sine 30 plus 0.5 meters, right? Because 50 centimeters is 0.5 meters. And that's equal to negative 32 mu. Mu we said up here to be 3.0. 3.0 times 10 to the negative 6 meters squared per second. Mu L, the length of the pipe is 3 meters, and then velocity 2 is what we're trying to figure out. And the gravity would be 9.81 times the diameter squared. Now the diameter we said to be 4 millimeters, and if we plug that in, that's 0.004 meters, right, for the diameter squared. And here we only have one unknown, V2. We know gravity, we know all of this. If we solve for V2, we get about 1.059 meters per second, okay? And let's check if this is laminar or turbulent, right? Because we assumed it to be laminar. Now we have the velocity, and we can figure out whether it's laminar or turbulent by the Reynolds number equation, right? Reynolds number is VD over nu. Now we have V, which is 1.059 meters per second. Diameter is 0.004, and nu is 3.0 times 10 to the negative 6. And if we plug all those in, we're going to get Reynolds number is about 1412. And that is certainly less than 2,000, meaning our assumption was right, and the flow through that pipe is laminar. Okay? So one more thing we need to figure out is the flow rate. The flow rate of the pipe. The flow rate is just Q equals VA, right? And the velocity we figured out to be 1.059 times the area. It's a tube, so it's pi over 4 times the diameter squared, which is 0.004 squared. And that's equal to 1.33 times 10 to the negative 5th meters cubed per second. Okay? That's in meters cubed per second. They want it in liters per minute. So we can just rewrite it here, times 10 to the negative 5th meters cubed per second. And remember, in 60 seconds, there's 1 minute, and in 1,000 liters, there's 1 meter cubed. And if we solve all that out, we get that the flow rate is about 0.798 liters per minute. Okay? And we'll do part B in the next video.